So for the synthesis of aldehydes and ketones, you kind of have to go back to all your functional groups that you've done before because you have done all of these syntheses before, okay, one way or another. So let's get started. So first is from alkenes, and you can take any kind of an alkene, whether it's highly substituted or not substituted, and cleave it with ozone. So this is called ozonolysis, and you can get two aldehydes or two ketones, or an aldehyde and a ketone, depending on what is substituted around the alkene. So in the top case here, where the alkene is completely substituted with carbons around, so when you cleave it, you end up getting two ketones, okay? And then if you have any kind of an alkene with hydrogens on it, then you will end up getting two aldehydes, okay? Now you can see the problem here with the second reaction, that if you have an asymmetric alkene, then you end up getting two different kinds of aldehydes. Now depending on what you're trying to do and what you're trying to make or what you are trying to achieve, if you're trying to synthesize an aldehyde, this may not be the best thing because, now you have to separate the two aldehydes. The top reaction is much better because you're getting symmetric cleavage. And so if you get symmetric cleavage, then you don't have to purify anything, right? So you just have to kind of distill it or crystallize your product and you're done, okay? But if you have two different things, two different products, then you have to kind of separate them out, okay? So unless you have boiling points that are very different and you can distill them, you may want to stick to something that is more symmetric. I'm just talking practical aspect now. Theoretically, this is awesome, okay? So all you have to do is just cleave an alkene in order to get aldehydes and ketones. From alkynes also you can make aldehydes and ketones depending on what kind of an alkyne you start from, okay? So if you have a terminal alkyne, you have more choices. If you have an internal alkyne, you have less choices, okay? So if you have a terminal alkyne, you can either make a ketone or you can make an aldehyde. You can make a ketone using mercury sulfate and sulfuric acid, or if you wanted to make an aldehyde, which is a terminal group, yet you have to use borane, okay, or any other reagent that's related to borane. You use that and you get an aldehyde. For that, you have to have a terminal alkyne. Now, this is considered like a Markovnikov product where you're getting a ketone, and then if you're using borane, this is kind of considered like an anti-Markovnikov because this is happening at the less sterically hindered carbon, okay? And so, you're not really exactly adding hydrogens, but still. Markovnikov and anti-Markovnikov, just to see where the group is going, okay, internal or terminal. But if you have an internal alkyne, now everything is symmetric. And so because of that symmetric, no matter what reagent you use, you're going to get the same product. Okay, so you have choices. If you want to make, an aldehyde, then you have to use a terminal alkyne, all right? But otherwise, you will get a ketone only. So that's from alkynes. Then alcohols here. This is my scheme of oxidation of alcohols, oxidation reduction of alcohol to aldehyde to acid. So in this scheme, we're going to deal with just the first part over here, okay, going from alcohol to aldehyde or ketone. So I have given you this one here. This is for the primary alcohol, right? So primary alcohol plus any kind of an oxidizing agent will give you aldehyde, but a secondary alcohol like this, if you oxidize that, you will get a ketone, okay? So secondary alcohols will give you ketones, primary will give you aldehyde. Now, primary alcohols, you have to be a little bit careful because primary alcohols can go all the way to acids, okay? If you oxidize them with the proper oxidizing agent, they can go all the way. So which means you are limited to your choice of oxidizing agent. In the case of secondary alcohol, you don't have any limitations, okay? Because once you oxidize the secondary alcohol, you get to ketone, which does not oxidize to acid, okay? So here, for secondary alcohol, you have more choices, all right? So I've given that over here in some, in sort of like a hint to you that here you can only use PCC for a primary alcohol. So primary alcohol plus PCC gives you aldehyde. Secondary alcohol, you can use PCC or sodium dichromate or KMNO4, whatever you want to use, weak or strong, it doesn't matter, you'll get a ketone. Okay, so here are a couple examples for that. I don't think there's anything more I need to say about this. Okay, moving on. So now we are at the other end of the scheme here for oxidation reduction. So now from acids, you can reduce the acid to give you aldehyde or a ketone. So here you have reduction. This is what we are focusing on, okay? But in this case, sad thing, bad thing, I don't know, whatever it maybe, it's nothing, it's just that you can only get aldehydes. Okay, you cannot form ketones this way. So acids are terminal groups, and any of the derivatives of acids, and I know we haven't quite done acids yet, but you can take an acid or you can take an ester also. So any of those, you can reduce those to give you aldehyde. You cannot get a ketone. Okay, over here also I've said that. So ketones cannot be made this way. So for taking an acid, you can either convert the acid into aldehyde, but generally synthetically, practically speaking, when you're working in the lab, you have to actually turn it into an acyl chloride and then do the reduction for it. Okay, so here is the one from ester. And in case you're wondering what kind of reducing agent do I need here, because remember, if you have a strong reducing agent, you will go all the way to the alcohol. Okay, so which means you need something weak enough, well, strong enough to reduce it to the aldehyde, but not strong enough to take it all the way. Okay, so LAH is out. Okay, so lithium aluminum hydride, you cannot use that because that will take the acid all the way to the alcohol. So here what we end up using is this kind of an aluminum reagent, which is kind of substituted with alkyl group, so it kind of makes it weaker. And then here's another one, diba, and this is the one that you can use because it has a nice shorthand, right? So you can easily use this one and remember this. But this is the structure for diba, which is diisobutyl aluminum hydride. So here the isobutyl group, aluminum, and then the hydride group. Okay, so again, I mean, lots of alkyl groups kind of turns down the potency of the hydride group. Okay, so it doesn't make it as strong. Lithium aluminum hydride would just straight up have 4 hydrides, okay, on there. So reduction of acids, but again, remember, this is only to make aldehydes, okay, and not for ketones. And then these two reactions we have done in aromatic chemistry, where you took benzene and did Friedel-Crafts acylation to give a ketone. Any R group can be anything, right? So any kind of an acyl chloride will give you a ketone. And then the Getterman-Koch synthesis is very specific for making benzaldehyde. So that is the synthesis, and that's from aromatic compounds. And I think that's about it for synthesis that we're doing right now.